Hello everyone, this is Professor Jeff Wilkerson with an introduction to Exercise 14, Lunar Features and Mountain Heights from Astronomers as Observers and Experimenters, published by Kendall Hunt. This is a lab book with laboratory exercises in astronomy, observing exercises in astronomy as well, for introductory astronomy. And this one in particular, we'll talk about a few things here with this one. One of our goals with the exercises in this text is to think about learning goals and think about learning outcomes and what those learning outcomes might be for a given exercise. And different people will look at these exercises and have different learning goals and or different emphases on the learning goals that are there. So two people might have the same learning goal or the same set of three learning goals, and have really want to emphasize one of those three. Person A might emphasize one of those three, person B a different one of those three, and person C a different one of those three, and then person D might have a completely different set of learning goals associated with the exercise. This particular exercise has a couple of learning goals that I really like to emphasize for my students. And one of those is one of the learning goals here, certainly one of the learning goals could be just understanding the sizes of features on the moon. And so thinking about how deep craters are, how big the features in the centers of craters are, for example, or how anything along these lines is certainly a reasonable learning goal to have associated with this exercise. One of the learning goals that I often emphasize with students is the human aspect of astronomy. And it seems like, to many of you, I'm sure it seems like this is old stuff and we've been doing this forever and we're talking about ancient ideas that have been around for a very long time. As you get older and you start to think about the evolution of our understanding of the universe, you tend to, that tends to shrink up just a little bit. And it's easier to feel yourself as part of the flow of what's going on, and as we've tried to understand the universe. That humans have been struggling to understand the universe for a long time, and we are now a part of that. You're partaking by doing these exercises and reading this textbook. You're now a part of that enterprise. You've always been a part of that enterprise, it turns out. It's the connectedness of humanity. But now you recognize that connectedness and you can see that. And so this is a great exercise because it has a tie directly to Galileo, where Galileo, when we think about the Copernican revolution and we think about developing universal laws that apply to everything in the universe, one of the great features of that movement, if you will, was sort of taking breaking down the barrier between what was perceived as heavens and what was perceived as earth, to say we are part of a physical realm, a physical universe, and the universe is ours, and that we are beings within that universe, and we are part woven into that universe. The laws that govern the universe are the physical laws that govern what we do here on earth. And a really key feature of that was Galileo beginning to understand that shadows on the moon were similar to shadows on the surface of the earth. And there's the photograph I took in your lab book, in this book, that you can see a shadow crawling across a valley floor here on the college's campus where I work. And it's all these years later, I'm still mesmerized by that idea, to see as the sun rises in the morning. That was a sunrise picture that I had in there, but a sunset picture would do the same thing. As the sun gets higher in the sky, that shadow length gets shorter, and you see the shadow move across the valley floor. So we're here in a valley, and as the sun comes up over here, the sun's coming out of the board, getting higher and higher. There's hills on this side, and the hills are ragged, and they're not all the same height, and there's trees of different heights on top of those hills. So you see a sunrise line, more or less, creep across that valley floor. This is in shadow, and this is in full sunlight. And you can see the stuff glowing in full sunlight. As the sun gets up higher, this line moves across this way, the terminator line. That's what we look at in this exercise, is the terminator. It's the sunrise sunset line on the moon. is that terminator line, and you see that move across here as the sun gets higher in the sky. Okay, now what's actually causing the sun to get higher in the sky, of course, is the rotation of the Earth. What's causing the terminator line to move, appear to move on the surface of the moon, is the rotation of the moon. And so we see a sunrise sunset line like that because of the rotation. But hopefully you've had a chance to observe this. And if not, take time to, the next time you do have that opportunity, to really appreciate that, to watch the sunrise line or the sunset line, the shadow line, move across the valley across the floor of a valley like that, wherever you happen to be. The deeper the valley, the more dramatic it is. But also, sometimes the deeper the valley, the harder it is to see that. If it's a wide, shallow valley, it's got a long distance to move across there. Anyway, take some time to appreciate that, and appreciate Galileo seeing this on the moon and saying, hey, I've seen this on Earth, and I've seen this kind of shadow moving around, and I see this in the craters on the moon, and I see this rock piles and mountains and features on the moon. I see those shadows. It looks like the same thing to me. Let's model this as the same thing. Let's say whatever causes the valley, the shadows on the surface of the moon, is probably the same thing that causes the shadows to move on the surface of the Earth. And we have rotating objects in the solar system, and we have the sun illuminating them. Let's run with that model and see what we can do. So this exercise ties you directly to that history, to that idea, and it's worth thinking about that bigger idea. Now, part of it then is that you have geometrical thinking going on. And for me and my students in class, one of the things we do is we emphasize geometrical thinking. It's not a kind of thinking that we've often participated in, that we've often really engaged in deeply in any meaningful way. And so we want to practice that geometrical thinking, because that's what Galileo was doing. He was actually, so he said, this is the idea. So one of the things that makes this astronomy a science rather than something else, we emphasize again and again and again that being right or wrong is not what makes it a science. It's the process you go through, the process you think about how you're going about trying to test whether this idea is correct or not. So that's what Galileo had to do. He had to test this model that what's causing the shadows on the surface of the moon is the same as what's causing the shadows on the surface of the Earth. What does that imply, at least? What implications come from making that model? And that requires some big geometrical thinking. And so you need to do this geometrical thinking. And it's not trivial geometrical thinking here. It's just, but this shows up other places too. We think about the geometry of the galaxy. We think about the geometry of the whole universe. We think about the geometry of the solar system as a flattened disk. What does that mean for the planets moving across the sky? So there's a lot of ways that we want to picture geometry in 2 or 3 dimensions and try to extrapolate from what we see in 2 dimensions on a page to 3 dimensions. And it tests our brain. And what we're doing here is pretty tricky, and we'll look at that just a little bit. So I've got a globe here for you. And so here's a globe, and you can see, imagine that what's facing you. Imagine the sun is where you are, and so noon is right around here facing you. The sunrise line is going to be, let me picture where we have, I'm looking right at an ocean. So the sunrise line is going to be over here, and the sunset line is going to be over here. And as the Earth rotates, you get noon, sunrise, sunset. You get new things rotating into daylight over here, and new things rotating into nighttime over here. So it's nighttime over here on the side of the Earth where I am. It's daytime over there that you're looking at on that side of the Earth. And if I take this piece of chalk and place it right here, so in a way that it's not covered up by my hand, perhaps, if I take this piece of chalk and I place it right here, you can see the closer that chalk gets to the sunset line, there it is, just about right on the sunset line. It's hard for you to see in my shirt, I think, there. There it is on the sunset line. As I rotate it towards you, now that we're rotating backward, try not to get queasy. You see it points more and more directly towards you. And you have longer shadows at sunset over here because the light of the sun is coming more directly at the perpendicular. The light of the sun is perpendicular to this object. It's getting closer and closer and closer to perpendicular to this object. And so you see the shadow get to be longer and longer and longer. What I want you to picture is to say that sunset line and the radius of the Earth coming out this direction. So if you picture the radius of the Earth coming out this direction and the sunset line right there, they're going to make a right angle. And this object is going to make a right angle with its shadow. The shadow is coming toward me right now. And if you look at that from the top, that shadow is coming out this direction. That's a right angle along this direction. And so that's what we've tried to represent for you in this figure, in the figures that you see right here from the textbook. And in particular, if you look at this figure right here, you see the shadow length here, and there's the right angle. That's the right angle that is between that right angle is between the radius of the moon, in the case here, but the radius of the Earth, and what I was just showing you is up this direction. This is the distance from the sunset line, and that's the drop down to the center of the moon down here. And so you see the center of the moon down here. Up here you see the right angle that is between the object that was making a shadow and its shadow there. So a couple of things. So what we want to practice is trying to reproduce that picture. We try to walk you through it here just a little bit in the text. It's hard to do. It's a little bit easier to do with three-dimensional models like this, maybe. And so this is relatively challenging geometrical thinking, but we'd like for you to practice that geometrical thinking just a little bit. It's a good exercise to be doing that practice. And again, so this is one of the learning outcomes, one of the learning goals we associate with this exercise is thinking geometrically. And you might be wondering right now, why do I want to think geometrically? I'm probably not going to have to do this kind of hard geometry ever again in my life. And that's a fair question to say, we don't, you never know. Maybe sometime you do have to do hard geometry when you're putting in a fence or something. I don't know. But to say you're probably right. You probably don't have to do this hard geometrical thinking. But if you practice it, it trains your brain to think in a certain way about problems, in a way maybe you haven't practiced thinking that way before. And your brain will actually function differently after having practiced this for a significant amount of time. So if we can do enough practice in the exercises in here of trying to figure out from a three-dimensional model, from a globe like this, how a figures like these arise, then we just might if we do that enough, we just might get better at it in a way that makes our brains function a little bit differently. And the next time we go out there and do whatever it is we want to do, whatever it is we're working on, whether that's some sort of accounting spreadsheet or that's some sort of, I don't know what that is, whatever that happens to be, we might think about it in a slightly different way. And it might be a more creative and interesting way just because our brain has been trained to think in different ways and to see different aspects. And that's true for thinking about big picture items like the whole universe, which pervades this entire textbook and the course on astronomy. So this is where we are with these learning goals. So what we'd like for you to do is to practice trying to reconstruct this picture right here and to say that the shadow length then is the AP that we have right here is proportional to the distance you are from the terminator line, from the sunrise sunset line. And the height of the feature is then proportional to the radius of the moon, so that we get this scaling relationship that we have right here that you see. And you can go in and measure several of these features and practice measuring to say, well, how deep is that crater based on how long that shadow is and how far it is from the terminator line. So the terminator line is right there, the sunrise sunset line. There's the shadow, just like the shadow in the valley floor that we drew up there. And we want to know how far that feature is from the terminator line and how long that shadow is. If we know the radius of the moon, then that's going to tell us how deep that crater is. You see another feature out here. If we get further away from the sunrise sunset line, and the features get smaller and smaller, the shadow lengths get smaller and smaller. It might be that crater right there and that crater right there, they are significantly less deep than this crater. But it might not be. It might just be that these things out here are so much further away that you can't, the shadows are much shorter because you're further away from that sunrise sunset line. Now, another thing that we emphasize a lot throughout this text is this idea of bias, observational bias, uncertainty, and uncertainty that might creep into measurements. And you might want to think about this related to this. How close do you need to be to that terminator line before this whole thing falls apart? Remember, we're measuring on the surface of a sphere here, and the moon is a spheroid anyway. And these heights are jagged, just like this line was jagged across here. And so, what causes you problems here as you go about trying to measure these things? And it's worth thinking through those things just a little bit. You want to measure these distances. As with many things here, you could do this with a ruler, but I recommend whenever you can to do this with a digital caliper. So you can go in here and just measure, span across the distance from the terminator line to the lip of that crater. And to say, well, where is the terminator line? Well, that's that jagged edge. It's kind of hard to tell. You're going to have some uncertainty in there. And so you want to measure as best you can across there and see if you can get your uncertainty in what that distance is. And you got to be careful if you measure up that direction. So you want to kind of come in perpendicular to the direction the sunlight's coming across there to reach the terminator line. And so you should be able to find several features on there and start to get a sense then of what a typical crater depth is, for example. Or you can see the shadow from this feature in the center of the crater where the object has hit the surface of the moon, created the crater, and you've got a little bit of pile up of material, a little bit of splashback of material there in the center of the crater. And you might be able to measure a few shadows like that to get a sense of what a typical depth of one of those, a typical height, of one of those objects is above the crater floor. And so that might be something you could work on. So there's several different things you could go and you could say, are they, one interesting, if you can do several of these, one interesting way to turn this into a bigger project, into a longer lab, is to measure a whole bunch of craters and to ask, what is the range of depths of craters? Maybe they're all about the same size, or maybe there's a wide range of depths, and that might be a research question you want to try to answer. And then you can ask the question, why would there be a wide range of depths, or why would they all be about the same size? Is the depth related to the diameter? Well, there's an interesting question that you could work on. You could say, let's measure the diameter of this crater and its depth. Let's measure the diameter of this crater and its depth, the diameter of this crater and its depth, the diameter of this crater and its depth, the diameter of this crater, this crater, this crater, this crater. You could measure 15 craters' diameters and 15 crater depths and ask, is there a relationship, or are those two variables not related to one another? And how certain are you of that relationship? And what kind of data would you want to take before you would become certain of that? That would be an interesting project. If you take your own pictures of the moon, that sunrise, sunset, that terminator line is going to move to different places across the moon. You could really get a whole bunch of data for a whole bunch of craters. You could turn this into a senior project kind of study that would be fun and interesting to do. Maybe I'll recommend that to one of my students. I'm standing here thinking of it right now. Every time I go through one of these exercises, I think about something new. Now, as we've talked about in some other exercises, maybe you've watched videos for those, maybe you haven't. This picture could have been printed at any scale. It could have been any size we wanted it to be. So, of course, if we blew this thing up so that it was the entire size of this board, of course, the shadow lengths are going to be longer on the picture. And so we need to know the scale of this picture. We could have shrunk it down to a postage stamp size down in here. And if we did that, then we would have shorter shadow lengths. The shadows would be smaller. So what you're measuring with your calipers is the length on this picture, and you need to scale it to the length of the actual depth of the actual size on the moon. You do that with the radius of the moon. So you need to know that the radius of the moon, OM, on this diagram, the radius of the moon is 267 millimeters. And so that gives you that value in here that allows you to do that scaling. So that's what you got. Good luck with this and have fun with it. Think about the long history of geometry and measuring in the solar system, and think about ways you could expand this and do some project kind of stuff like we just talked about. Say you could turn this into an entire semester long project that would be fun and fantastic if you had the ability to take some pictures of the moon over different phases. So anyway, that's your introduction to exercise 14, lunar features and mountain heights. Good luck, everybody.